Unit 6, Lesson 6, the Fundamental Theorem of Calculus and Definite Integrals. We have now seen the two major branches of calculus. Number 1, differential. Number 2, integral. Leibniz and Newton independently discovered a connection between these two branches, stated informally that differentiation and indefinite integration are inverse operations. In an earlier lesson, we used the Fundamental Theorem of Calculus Part 1 to define new functions, represent accumulation functions, and provide information about the antiderivative function. So the Fundamental Theorem of Calculus Part 1, if f of x is continuous on a closed interval ab, then g of x equals the integral from a to x f of t dt. Is continuous on the closed interval AB, and it is differentiable on the open interval AB. Also, g prime of x equals f of x. So an alternate notation can be seen by taking the derivative of both sides. And so anytime you see that derivative of an integral like that, I guess, more specifically just this piece right here, right? The derivative of the integral. They undo each other. So notice that basically what they've done is they've taken this and they've put it in for t. And they give you this. If this x had a derivative other than 1, you would have to multiply it by that. So that means that if I was taking the derivative of the integral from a to x cubed, let's say, f of t dt, the derivative here and the integral here, they cancel each other out, kind of. So, we're going to still say that this is f of x cubed, but we have to multiply it by the derivative of that, which would be 3x squared. So this, I would always bring this in front, 3x squared times f of x cubed. And so whatever your f of x is, you turn it into f of x cubed. So that's the only other thing you have to remember here, is that this a has to be, a number, or, some sort of number. It's signifying the first part of your integral, or interval, and it's going to just some x value. If this x value that it's going to has a derivative that is 1, then you're just putting that in right here to get this answer here, okay? But if that has any other derivative, like I showed you over here, then you have to multiply by it, just like we would with the chain rule. So in words, we can say the Fundamental Theorem Part 1 says that if we define a function as the definite integral of another function, then the new function is an antiderivative of that function. Now we want to turn our attention to the Fundamental Theorem of Calculus Part 2, which will give us a tool for computing definite integrals in a quick and efficient manner. Given that f represents the rate at which the function f of x is changing, that is, f of x, little f of x equals capital F prime of x, we know that the integral from a to b, f of x dx, represents the total net change in capital F on the interval AB. So we're talking about the total net change. That's what this integral represents. So, Fundamental Theorem of Calculus Part 2. If a function f is continuous on a closed interval AB, and capital F of x is an antiderivative of little f on the interval AB, then the integral from a to b, f of x dx, is capital F of b minus capital F of a. If you like, you can also write this as the integral from a to b of g prime of t dt equals g of b minus g of a. Remember what I said, that when you have an integral sign and you're looking at this function right here, it's always the derivative. Your answer is going to be your original function. That's why they put g here, because they're referring to the original function, that if you took the derivative of this g function, you're going to get this g prime that you actually had as the integral function. In words, we can say the definite integral of a function over ab, closed interval ab, is equal to the net change or displacement in the antiderivative of f over the same interval. This is commonly known as the evaluation theorem. Okay, so now, using proper notation, we're on the next page. When applying the fundamental theorem of calculus, we will follow the notation below. The integral from a to b f of x dx equals capital F of x, and then we put that vertical line here, meaning at. So that vertical line there, it means at. Oh. Well, erase that. Sorry about that, guys. It means at, evaluated at, maybe we should say, evaluated at a to b. And then our rule is evaluated at the top minus the evaluation at the bottom, okay? But that vertical line means like evaluated at. All right, example number 1. Find the value of the definite integrals by using the evaluation theorem stated above. So, remember that we said if we were integrating x to the n dx, it would be x to the n plus 1 divided by n plus 1, okay? And since this would be a definite, an indefinite integral, you would have to add a plus c. But if it's a definite integral, x to the n dx, then it would be x to the n plus 1 divided by n plus 1 from a to b. And so this is your indefinite integral that you have to add the plus c because there's no a to b there. This is your definite integral. But either way, you're going to do x to the n plus 1 divided by n plus 1. So this is going to be x to the 2 plus 1, which is x to the 3, divided by 3. And then minus 3 is going to be minus 3x from 1 to 2. So I'm saying from here. I was thinking I said evaluated at, but oh well. Either way, so you're going to take that whole thing at 2. So you're going to say 2 to the third over 3 minus 3 times 2. So notice I put 2 in for my x value minus, now I'm going to put 1 in for my x value. 1 to the third over 3 minus 3 times 1. And so this is going to be 8 thirds minus 6 minus 1/3, because I went ahead and took this negative and distributed it here. I'm going to distribute it also here, giving me plus 3. So that's 7 thirds. I took the 8 thirds minus 1/3, got 7 thirds, and the negative 6 and the positive 3 is a negative 3. Now I'll just make that 7 thirds minus 9 thirds, which gives me negative 2 thirds. And just to kind of get an idea of what they're saying here, this is 1, 2, 3. This is the function x squared minus 3. Y equals x squared minus 3. And so they want to know what it is from 1 to 2. And at 1, we'd have negative 2. And at 2, we'd have positive 1, right? 2 squared is 4 minus 3. Okay? So they're saying that if you took the area under the curve, which is like this area, should have used a different color, sorry. But the area, so from, and I don't know where it crosses the x-axis. Where does it cross the x-axis? How about at square root of 3? So from 1 to the square root of 3, it's all negative. But from the square root of 3 to 2, it's positive. Well, when you add those together, you're going to get negative 2/3, right? So some of it's going to be negative, some of it's going to be positive. But when you add them together, there's more negative than there is positive. Okay, just so you can kind of understand that this is what that means. We integrated this x squared minus 3, which is the derivative function, from 1 to 2. Okay, and we used and you can think of it as you're looking at, the derivative function, the area between 1 and 2. The area from 1 to 2 between the function and the x-axis. All right, let's look at the next one. We can bring that 3 out front. 1 to 4, we can make this x to the 1/2. And then we've got a 3 out front. Remember, this is x to the 1/2 plus 2/2, because we're adding 1, only we're going to make our 1 2/2. So this is going to be x to the 3/2. And then we're going to divide by 3/2, which you should know. And then from 1 to 4. But when we divide by 3/2, it's the same thing as multiplying by 2/3. From 1 to 4. Okay? So you can see that the 3's will cancel. So this is going to give us, I'm going to go like that and continue this down here. 2x to the 3/2 from 1 to 4. And when I see the 2 in the denominator, I think of square root. So I'm just going to say square root of 4, 2 times square root of 4 to the 3rd minus 2 times square root of 1 to the 3rd. So 2 times 2 to the 3rd minus 2 times 1 to the 3rd. 2 times 8 minus 2, 16 minus 2, 14. And again, if you wanted to think of it as and I think this is kind of stretched up like that because it's, let's say that this is y equals 3 times the square root of x from 1 to 4. So this point would be at y equals 3, and this one would be at y equals 6. So not the greatest graph there, but you can imagine that we just found that area from 1 to 4. Okay? All right. Here's our next one. Since we don't really know how to integrate a function where it's 2x minus 1 to the 2nd power, we're going to go ahead and multiply that out, and we're going to get 4x squared minus, I got a minus 2x and a minus 2x, which will give me a minus 4x plus 1 dx. So that's what we're going to start out with. Then, when we're going to integrate, we've got 4x to the 2 plus 1, so x to the 3 divided by 3. minus 4x to the 1 plus 1, so squared, divided by 2. And then this would just be plus x, right? From negative 1 to 1. And so we could divide by 2, make that a 2. And now we're going to evaluate it at 1. So this would be 2 times 1 squared plus 1 minus the evaluation of this whole thing at negative 1. So I am just putting a negative 1 in wherever there's an x. Okay. I keep running out of space, guys. I'm sorry. So I'll just kind of go down here. So this is going to be 4/3 minus 2 plus 1 minus, this is going to be negative 4/3 minus 2 minus 1. So I've got 4/3 minus 2 plus 1 plus 4/3 plus 2 plus 1. And so I didn't combine that negative 2 and that positive 1 there because I knew that, oops, I canceled out too many. Sorry about that. I knew that negative 2 and that positive 2 were going to cancel. Okay. I accidentally marked on my ones. All right, so that gives me 8/3 plus 2, which is going to be 8/3 plus 6/3, because 2 is 6/3, and that gives me 14/3. Okay, so this one is 14/3. Just go like that. Okay. All right, now D. What can we take the derivative of that will give us sine? Hopefully you will think negative cosine. If I take the derivative of negative cosine, it's a negative times a negative sign, which gives me positive sine. And then plus x from 0 to pi. So this would be negative cosine pi plus pi minus negative cosine 0 plus 0. And on the unit circle, here's my pi. And this point is negative 1, 0 cosine sine. So this is minus a minus 1, because this minus is the first one, and then the cosine of pi is negative 1. Plus pi, and then minus a minus is a plus, and then the cosine of 0 is 1. Okay, plus 0 doesn't matter. So we've got, excuse me, 1 plus pi plus 1, 2 plus pi. That's the area. Okay, letter E. This one, we're going to have to be careful. We have to simplify it a little bit before we can integrate. So if I have the integral, or I mean the square root of a over b, I can make it the square root of a over the square root of b. Okay, so I just did that. I just made the square root of a over b, square root of a over square root of b. I can bring this square root of 2 out front, and then I'm left with 1 over x to the 1/2, and then I want to bring that up as x to the negative 1/2. So now I can integrate, because I can say x to the negative 1/2 plus 2/2 divided by negative 1/2 plus 2/2, right? And that is from 1 to 8. So square root of 2 times x to the positive 1/2 divided by positive 1/2 from 1 to 8, which is going to be multiplication by 2. So instead of division by 1/2, it's the same thing as multiplication by 2. So I just put that 2 in front of the square root of 2. So now we've got 2 square root of 2 times the square root of 8 minus 2 square root of 2 times the square root of 1. So 2 square root of 2, and then the square root of 8 is the square root of 4 times the square root of 2 minus 2 square root of 2. So look, this is 2 times 2, right? Because this right here is 2. So 2 times 2 is 4. And then the square root of 2 times the square root of 2 is the square root of 4, which is also 2. I feel like I'm saying the same thing a bunch of times. But anyway, that would simplify to 8 minus 2 root 2 for the integral in E. All right, and here I want you to recognize that this is a monomial. And if you have a monomial in the denominator, you can separate it out into both of, the terms in the numerator. So this can become the integral from 1 to 4 of x over the square root of x minus 2 over the square root of x dx. So if we do it like that, I have x to the 1, which I'm going to make x to the 2/2 over x to the 1/2. Henry, stop. Minus 2, this is going to be x to the negative 1/2 dx. So we're almost there. I want to bring this x to the 1/2 up. It's going to become x to the negative 1/2 up there. And since they have the same base, you'll add them. So this is going to be x to the positive 1/2 minus 2x to the negative 1/2 dx. So now we're going to use our x to the n, so that's x to the 1/2 plus 2/2. So that's going to be x to the 3/2. Division by 3/2 is multiplication by 2/3. Minus, and this is going to be 2x to the negative 1/2 plus 2/2. So that's going to be x to the 1/2. And then divided by 1/2 is multiplication by 2 from 1 to 4. So I'm starting to go a little bit faster with these integrals, and I hope it's not too fast. It might be, but if you have to write it out like I did over here, go ahead and stop the video and then just, because really this is the first time right here that I didn't, do it all, written out for you. So hopefully, if you have to stop the video, it's fine. All right, so now 2/3. And then, of course, this denominator of 2 tells me that's a square root. And I'm going to do the 4 first because it's the top number. And then this would be, because it's 3/2, that would be to the 3rd power. Minus 4 times the square root of 4. So there's my putting 4 in for x. And then minus, now I'm going to put 1 in for x. And if you have 1 to any power, it really, it doesn't matter what power 1 is being taken to, it's always going to give you 1, okay? So I don't even have to go through the square root thing with that. So now you've got 2/3 times 2 to the 3rd, so that'd be times 8, minus 4 times 2, because root 4 is 2, minus 2/3 plus 4. And so this is going to be 16 thirds minus 8 minus 2 thirds plus 4. And again, I already distributed that negative, right? So this is 14 thirds minus 4, because 16 minus 2 is 14, and then a negative 8 and a positive 4 is a negative 4. So this is 14 thirds minus, this 4 would be 12 thirds. So 2 thirds is what I get for E, or for F. So there's my answer, 2 thirds. Okay, so now, example number 2. Total change concepts and explaining an integral in real-world terms. So part A, if f of t represents the rate at which your 401k changes in value over the month of January, units of f of t, which would be dollars per day, dt, days, f of t dt would be dollars. So this is what we're saying, that when you integrate something, it is a derivative, right? And a derivative is a rate of change, okay? A derivative is a rate of change. That means it's something per something. And dollars per day is what this situation would be. With respect to days, like, whatever this dt is, well, what does your t represent? Days. When you take and you get the answer, it's just going to be in whatever your numerator is of your rate of change. Your answer is going to be in dollars, okay? If it were miles per hour that you were integrating, your answer would be in miles. If it were feet per second that you were integrating, your answer would be feet. Okay, so just things like that to think of whenever you've got a real world problem, because a lot of times what it's asking you for is what is going to be, like looking at the units, it's going to help you understand what to do to solve it when you look at the units. So, like, if they gave me, okay, this function is some sort of rate of change function, and they then asked me to find whatever it is, that's in the numerator. If they asked me to find dollars and they gave me dollars per day, I knew I'd be integrating. So that's the kind of thing that you want to be looking for. It helps you figure out what to do with the problem when you're not sure. Am I going to take the derivative? Am I going to integrate? So the integral from 1 to 31 f of t dt represents the total change in the value of your 401k in dollars for the month of January, because it went from 1 to 31, and January has 31 days. Okay, so if R of t represents the rate at which your pizza changes temperature in a 475-degree pizza oven 5 minutes after the pizza had been placed into the oven to cook. So R of t represents the rate at which your pizza changes temperature. So it's going to be degrees Fahrenheit per minute, right? That's the rate at which it changes temperature 5 minutes after the pizza had been placed into the oven to cook. So the integral from 5 to 20 R of t dt represents the total change in temperature of the pizza in degrees Fahrenheit from T equals 5 minutes to 20 minutes. So if they're times 0, because they're saying 5 minutes after the pizza had been placed into the oven. So if their times 0 is 5 minutes after, 5 minutes later here would be 10 minutes, right? So I don't think this was worded so wonderfully, but if it did mean that, then this would have been from 10 minutes, because you'd have to add a 5 onto each of these, to 25 minutes, okay, which, I don't know. I did put a little note there that I felt like that wasn't worded so great. So, you know, you just want to be careful. Hopefully I will word it better, or they will word it better in the future on your homework and things like that. You and your friends are planning to buy a ticket to your favorite music group, the Newtons. Everyone wants to hear their latest hit. Why integrate? If A of t represents the rate at which students are arriving at the ticket window, and P of t represents the rate at which they buy their tickets and enter the concert, then the integral from 1 to 5, A of t dt represents the, now remember, this is the rate at which the students are arriving at the ticket window. So it's going to be students per whatever the time is. And so, did it tell us time here? So when you integrate, since this is going to be students per time, you're going to integrate, and it's going to be students. So this is going to represent the number of students arriving to get in line. From t equals 1 minute, I guess t is in minutes, to t equals 5 minutes. It's the rate at which they're arriving at the ticket window. So the number of students arriving to get in line from t equals 1 minute to t equals 5 minutes. The integral from 1 to 5, P of t, represents, so P of t was the rate at which they buy their tickets and enter the concert. So this is going to be the number of students that have bought tickets and leave the line on the t from 1 to 5 minute interval. And then A of t minus P of t is the rate at which, so those are both rates, the rate at which the line is growing. Or shrinking, because you're subtracting off the people who got their tickets and went into the concert. So the rate at which the line is growing or shrinking. And then the integral from 1 to 5, a of t minus p of t dt represents the total change in the number of students in line on that 1 to 5 minute interval. So recall that the velocity v of t represents your velocity where the positive direction is to the right. So velocity is a rate at which position is changing. And the integral from 5 to 50 v of t dt represents the total change in position on that 5, 50 unit interval, which has a special name in math called displacement. Likewise, a of t is the rate at which velocity is changing. So you remember that we have called the position function a lot of times s of t. We've called the velocity function, which is the derivative of position, v of t. And then we've called the acceleration function, which is the second derivative of position. It is the first derivative of velocity. We call that a of t. Okay, so this you really just need to always know. I think you do, I hope. But when you integrate velocity, you get displacement. Okay, so, you know, velocity is like feet per second. Position is like feet, you know, so when you integrate feet per second, you get feet. When you integrate feet per second squared, you get feet per second. Okay, so the fundamental theorem of calculus, special cases. So far we have seen that when given capital F of x equals the integral f of t dt, f of t has always been the derivative of f of x. In the next example, we will want to explore some special cases where f of t may or may not be the derivative. We want to find a general rule for evaluating expressions such as, so see how we're taking the derivative of the integral from a to g of x, f of t dt. So in other words, we can't, why can't we say the result is always going to be f of g of x? This is where the chain rule comes in. Okay, that's why we can't just say that. So find the derivative in two different ways. Will your result always be f of x equals f prime of x? So case 1, capital F of x is the integral from pi to x cosine t dt. And so first thing we're going to do is we're going to say, what can we take the derivative of that will give me cosine? And that would be sine. So I know that this is going to be the sine of x from, t. Well, okay. Probably should have said the sine of t because I'm integrating. I'll change that. Sine of t from pi to x. So we get sine of x minus sine of pi. We know that the sine of pi is 0. So this just gives me sine of x. And so if I said, okay, so my f of x is the sine of x. And if I find my f prime of x, it's going to be cosine x. So for this one, my little f is my f prime of x, right? Because this was considered my little f here. That was my little f, okay? And so we just proved that for that one it worked. Number 2, they want us to take the antiderivative. Okay, so this is 1 plus t to the 1/2 power. And I'm going to go ahead and use, this one's so fat. This is the same thing as the integral from 0 to x cubed of 1 plus t to the 1/2 dt. Now, what is the derivative of 1 plus t? It's just 1. So if this base right here that we're talking about has a derivative of 1, we can use the x to the n rule. So we can say 1 plus t to the 1/2 plus 2/2, and then divided by 1/2 plus 2/2 is the same thing as multiplying by the reciprocal. So that is your antiderivative from 0 to x cubed. So this is going to be 2/3 times, 1 plus, sorry, got ahead of myself there, 1 plus x cubed to the 3/2 minus 2/3 times 1 plus 0 to the 3/2. So I guess you could, I don't know, let's just leave it 2/3 1 plus x cubed to the 3/2, and then 1 to any power here is going to be 1 times negative 2/3, so this is negative 2/3. Okay, so that's what I get. This is my capital F of x. And then we take my capital F of x that we just found, 2/3 times 1 plus x cubed to the 3/2 minus 2/3, and we take the derivative of it. So I'm going to bring my 3/2 down times my 2/3, and it's going to give me 1. So that gives me, bringing that down times this to the 3/2 minus 2/2. So that's going to be to the 1/2, and then times the derivative of 1 plus x cubed would be 3x squared. And then the derivative of negative 2/3 is 0. So you can see that for this one, it is not true, okay? Because this would be 3x squared times the square root of 1 plus x cubed. So my f prime of x here is not equal to my little f of x, which was the square root of 1 plus t. Okay, so for that situation, and I hope that since I've already told you a little bit, you know why. Because this was not just an x like it was up here. Okay? And so hopefully you're seeing that, hey, in the end, we're trying to take this f of x equals the integral from 0 to x cubed square root of 1 plus t dt, and we're trying to say, hey, I want to take the derivative of both sides. And if you're taking the derivative of both sides here, this is going to give you capital F prime of x is going to equal, remember I said that the derivative and the integral cancel each other out, and that you are going to be putting your x cubed in where your variable is, but then you're going to have to multiply by 3x squared. So if you're taking the derivative, 3x squared times the square root of 1 plus x cubed. would be. And that's what we got when we did it, you know, when we did it the weird way, but you want to be able to do it this way. You know, they're trying to show you and make you prove why this is true so that you won't forget it. But you can look here. Well, now this one's really weird because it doesn't have a constant on the bottom. So if it doesn't have a constant on the bottom, there's another thing that you have to do. And I haven't talked to you about that yet. And so this is where your upper bound is a function of x and your lower bound is a function of x. So you should, when you see that, you should think danger, danger, danger. Because your rule only works when those are, when the bottom one is a constant. So what we're going to do is we're going to kind of split it up. We're going to say, hey, I'm going to go from x squared to some a, and then I'm going to go from a to cosine x, because I want to use my rule for a constant. And then since I need the constant to be on the bottom, I'm going to say negative integral from a to x squared plus integral from a to cosine x. And now they want us to integrate, so we're kind of doing it the other way, right? We're trying to, you know, play the game of showing that, you know, making sure we prove that it's not, that it is correct or it isn't. This one was good. This one wasn't. So we're going to try it this way. So what would be the integral? What can I take the derivative of that will give me sine? That should be negative cosine from a to x squared. And then, again, negative cosine from a to cosine x. So minus a minus gives me a positive cosine. I would say cosine x squared minus cosine a, using the fundamental theorem of calculus. This one would be negative cosine of cosine x. And then minus negative, so that'd be plus cosine a. So my negative cosine a, my positive cosine a go away, and I'm left with cosine of x squared minus cosine of cosine x. And so that is my capital F of x. So I'm going to rewrite that up here and then try and take the derivative of it. So I've got cosine of x squared minus cosine of cosine x. And I want to take the derivative of that. So cosine of x squared is negative sine of x squared times the derivative of x squared, so times 2x. And then minus the derivative of cosine is negative sine of cosine x times the derivative of cosine x, which is times negative sine x. Sorry, I had to squeeze that in. And so negative 2x sine of x squared, this would be negative times negative is a positive, but then you've got this negative in front. So this is negative, and I'm going to bring that sine x times sine of cosine x. So that's kind of a weird, but it's sine x times sine of cosine x. And so now you can see that that was not what you started with. Look, this was your capital, or that was your little f. So that obviously your little f does not equal your capital F prime, okay? And so, again, you know, if we would still, you can still split this up, but do you see how here it would have just been, if you were, right away taking the derivative of both sides, you would have put sine x squared in and then multiply by the derivative of x squared. And then here you would have put sine of cosine x in and then multiply by the derivative of cosine x. Okay, so hopefully that makes sense to you on what to do whenever you're taking the derivative of an integral. And that's something that you need to practice, and it's something that you can really mess up easily. So please be careful with that. We've only got 2 pages left, but I think I'm going to take a little break. I don't know. Should I take a break? I don't know. I guess you guys can stop it. I know it's getting long. I feel like I've been talking for a while. So I guess you guys can stop it if you want to. I'm going to go ahead and keep going. All right, sometimes, always, never. Can you see the need for the chain rule in some cases? So the derivative of the integral from a to g of x, f of t dt, equals f of g of x. Well, sometimes it does if your g of x has a derivative that's 1, right? Because if g of x has a derivative of 1, then this would be true. If it has a derivative of anything other than 1, though, you have to multiply it by that derivative for this to be true. So the general form for Fundamental Theorem of Calculus Part 1, the derivative of the integral, is this, okay? So there it is. I added it on up there, but the only time the one above would have been true without me adding that on is if, and we could write that, instead of going like that, let's say, true, comma, if g prime of x equals 1, right? So that's when it's true. If g prime of x equals anything other than 1, you have to use this, okay? So the derivative of the integral from a function to a function ends up being f of g of x times g prime of x minus f of h of x times h prime of x. So that's another general form. So example number 4, find the derivative f prime of x given that f of x equals the integral from 0 to x squared e to the t squared dt. So if I want to take the derivative of f of x and take the derivative of the integral, this is going to give me f prime of x is equal to, and really, I like it better. I don't want to put that other equal sign there, so I like it better doing it like that. So derivative of the integral. So what I do is I take and I put my x squared in wherever my t is. So this is going to give me x squared squared, which is x to the 4th, right? 2 times 2. And then times the derivative of x squared, because this was not, it did not have a derivative of 1. So the derivative of x squared is 2x. So that makes my f prime of x equal to, and I always like to bring this in front, 2x times e, oops, accidentally put negative, sorry, I don't know why, e to the x to the 4th. Okay? So that is your derivative. Evaluate the integral if possible. The integral from -3 to 6. And what I think of is -3 to 6 includes 0. But look, that part of your function is not defined at 0. So I'm going to say notice on the closed interval from -3 to 6, the 2 divided by x term is not defined at x equals 0. So the integral cannot be evaluated. And I just put like a star. Function goes to infinity. And negative infinity. On both sides of 0. So you cannot split up into 2 parts unless you use an improper integral, which we don't do improper integrals until Calc 2. So you'll do an improper integral in Calc 2, because what you'll end up having to do is go from -3 to 0, blah, 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 dx, and then plus 0 to 6, blah, 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 dx. But then since it goes to infinity here, you have to do a limit as b goes to infinity of the integral from -3 to b. You know, so you make these into limits. That's what an improper integral does. Oh, and this would have been as a goes to infinity. So this would have been a to 6, right? But anyway, you don't have to know that. I just thought some of you might be curious. Okay, so we were not able to evaluate that one. Example number 6, evaluate the integral 0 to 4, 2x minus 5 dx. So if I was, trying to figure this one out, I would say, okay, well, 2x minus 5 equals 0, 2x equals 5, x equals 5 halves. And so this function, if I put a 5 halves in, I'd get 0. So here's 1, here's 2, here's 3, here's 5 halves. Okay, that's what that function looks like. And we're trying to evaluate it from 0 to 4. So we have a place where we're going to have to split that up. So what we would do is we'd say, okay, well, I can integrate it from 0 to 2.5, or 5 halves. I just put 2.5 this time. Absolute value of 2x minus 5 dx, plus I can integrate from 2.5 to 4. Absolute value of 2x minus 5 dx. Okay, I would have to split it up there because it's not differentiable, right? It doesn't have that. It has a break there. So when you are integrating here, you would get x squared minus 5x from 0 to 2.5 plus x squared minus 5x from 2.5 to 4 and we've got 2.5 squared minus 5 times 2.5, and then if I put 0 in, I'm just going to get 0, plus, and this one's going to be 4 squared minus 5 times 4, that minus my 2.5 squared minus 5 times 2.5, and So after, you know, putting this in your calculator, I think you guys can see that you get 6.25 plus, and then this one would end up giving you 2.25. So you would get a final, because this one would have been basically that area plus that area. And I don't know if my graph is completely, you know, right, but something, it'll look something like that. And 8.5 should be what you get. Okay, so integrating a piecewise function. Example number 7, consider the piecewise defined function whose graph is shown at the right. So we've got, for less than or equal to 1, we have and so there's a solid dot there. We have the 3x squared parabola, and then we have 5, so there's an open circle right here, and it goes that way. Everything greater than 1 is just 5. So we're going to integrate from 3 to 8. Well, from 3 to 8, you know, you've got 3, and then it's just going to be 5. That's just going to be a rectangle, right? We're going to go ahead and say this is the integral from 3 to 8 of 5 dx. So this is 5x from 3 to 8. So 5 times 8 minus 5 times 3. 40 minus 15, 25. Okay. And then from negative 2 to 4, so I've got negative 2, you know, that is this, and then, oh boy, you know, so like everything here is negative 2 to 1 is fine. It's that function. But then I would have to do 1 to 4, this other function, okay? So we're going to have to split this up. So from negative 2 to 1, I can integrate 3x squared dx. But then from 1 to 4, I would have to do 5 dx. Okay, so we've got x cubed here from negative 2 to 1 plus 5x from 1 to 4. So 1 cubed and then minus negative 2 cubed. That takes care of that first one. Plus, this is going to be 5 times 4 minus 5 times 1. So 1 minus a minus 8 plus, and this would be 20 minus 5, 15. So 1 plus 8 plus 15, 24. Okay. And now integration with a calculator. This one, if f is an antiderivative of cosine x squared over e to the x, such that f of 1 is 1/3, find f of 0. So we're going to look at this as the integral from 0 to 1 cosine x squared e to the x dx. And that's going to be my f of 1 minus my f of 0. So if I put this in my calculator, this left-hand side, I know that my f of 1 is 1/3, and I could find my f of 0. So if you go to your Desmos calculator, or you can go to your calculator that's in your hand, and I will put function, miscellaneous, integral, and I would put from 0 to 1, and I would put function, trig, cosine, x squared divided by e to the x. I don't know if they have an e to the x here, exponential to the x. I don't know if that's right. e to the x. And then we go to here and do dx. Okay, so that's what I got on my paper, also 0.59005. So I'm going to go back to our notes here. I just wanted to show you how I did that. And so here I got, I got 0.59005099 is what I wrote. And so then I subtracted 1/3 from both sides. And then I, divided by -1, which gave me f of 0 equals 1/3 minus 0.59005099. And then I put that in my calculator and got approximately negative 0.2567. So example number 9, unleaded gasoline is being pumped into an empty underground storage tank for the opening of a new convenience store at the rate of 600 times the square root of t gallons per hour. How many gallons of gasoline can the supply truck deliver if the driver pumps for 2 hours? So look, this is gallons per hour. This is a rate. This is a rate function. If I integrate the rate, I'm going to get gallons because that's the numerator of my rate unit. And it's asking how many gallons. That tells me I need to integrate. And it says per hour for 2 hours. So he's integrating, we would be integrating from 0 to 2 because he's pumping for 2 hours. And this would be 600 square root of t dt. So if you want to think of it as, that's your velocity function, right? This is going to give us the number of gallons of gasoline, right? If we integrate this from 0 to 2. So I called it V. I don't know if I called it V for volume, but it's just going to be in gallons. So I'm not sure why I called it V. So you don't have to call it V. You could call it G for gallons or G for gas. I don't care. I called it V on my paper for some reason. But so think of this as integral from 0 to 2, 600 t to the 1/2 dt. And so this 600, stays there, and this is t to the 1/2 plus 2/2, and then divided by 1/2 plus 2/2, which is going to be, from 0 to 2, which is going to be the same thing as multiplying by 2/3. So this is going to be 600 over 1 times 2/3, t to the 3/2 from 0 to 2. So divide by 3 is going to give us 400, 200 times 2, 400 t to the 3/2 from 0 to 2. So 400 times the square root of 2 to the 3rd minus 400 times the square root of 0 to the 3rd, which we know that is just going to go to 0. So that one's just going to go to 0. Square root of 2 times the square root of 2 is 2. So that's 800 times the square, and then there's one more square root of 2 left. So 800 times the square root of 2 gallons is your answer. And if you put that in your calculator, that is approximately 1,131.371 gallons. Okay? So there's exact answer, and this one is the approximate one. And we integrated gallons per hour